Okay, hello, can you hear me? Okay, I think this is online. Would like to start the live. Okay, so this is 10 p.m. in Japan time. Hello, this is Junichiro Horikawa, and this is the weekly tutorial live for Houdini that I've been doing using algorithmic design method and called as Houdini Algorithmic Live, and this is the 60th episode for the live. And the topic for today is to create a kind of bit of a quick and dirty way to create a quadrilateral remesh, from any kind of geometry that you input, which in this case I'm using this kind of, first of all I have this kind of geometry, then using either way, either a recursive method, either using a for loop or a solver to create a quad remesh without using any kind of plugins like these. Or you could also see its iterating smoothness of this quadrilateral remesh by using a solver as well. And the thing is, as you can see, it is a quadrilateral faces that you can create with this method, but it's not that clean as compared with other like sophisticated plugins like Exoside, a Quadremesh plugin, which is a paid plugin for a Houdini to do a Quadremesh like this. But the purpose of this tutorial is just to show some a rather easy process to create this kind of a remesh geometry, having these quadrilaterals, quad faces from any kind of geometry as a starting point. Maybe when you want to implement these kind of stuff by yourself. And I think the idea could be transferred into any kind of like softwares, including like game engines, so it might be useful in some cases, although the quality is like these. So decide if you think it's useful or not. I'll show you other examples. For example, if it's like a plane or a pig head. Was it a pig head? Looks like these. It's not that bad, I think. Although I still have these kind of connections which has 3 sides. The best quad remesh has a least number of these neighboring of 3, but having neighboring of 4 quads is the best situations as much as possible to have these kind of because if you add the angle for each of the angle for each corners for each neighbors, you have 90 degrees, and that's the kind of angle you really want for the quads. But for those, because there are 3 neighbors at each point, you have like 120 degrees for each corner, which makes you a kind of a twisted angle like these. If it gets more than 4, then you have less than 90 degrees. So that's kind of a that also makes the quad's face a bit deformed, like this part. So you do have some parts which have these kind of situations. If it's a plane, it looks like these. If it is a sphere, it looks like these, and so on. Though I found the method could be really useful for some cases, so let me show how you can implement this from scratch for any kind of geometry. Alright, so bring this back to the top. So let me explain how I can do this. Right, so first thing first, I think I'll show you the algorithm that I have used to implement in this one. So if you are good enough, fluent enough in Vex or any kind of programming languages, you'll be able to like implement yourself by understanding the underlying algorithm. So let me write some sketch here. Hello everybody. So first thing first, what you're going to have is this kind of any kind of face that you want to remesh, okay? And initially it could be any kind of, could be a grid, could be already like remesh with the triangles and so on. And the first thing I am going to do with this one, to make it quick and dirty, I'm going to rely on some of the functions that Houdini has, which first of all, what I'm going to use is the triangular remesh node. So you can easily create a triangular remesh in Houdini with the default component. So what I'm going to do is to create this triangular remesh using its default node. And probably if you want to create more a gradient like remeshing stuff, you could also use a adaptive remesh options. Okay, that's the first step. So step 1, triangle remesh. And if you don't want to use the node itself, I think you could do some other ways. It could be a bit more dirty and a bit more slower, but making triangle remesh is much easier than quad, for sure. Okay, and after you have created the triangle remesh, what I want to do next is to, first of all, I would like to have as much number of like quad neighbors as possible, like 4 neighbors for each point as possible, meaning, as I said, if you look from the top, like these, for each points or each vertices on the mesh, I would like to have 4 corners for each points, like 1, 2, 3, 4, as much as possible. If you have like 3 neighbors, then it will look like something these, okay? So to avoid having like these, it's it's a good idea to define some kind of flow on a mesh. For example, in this kind of mesh, if you have a curve like if you have a curvature like these, you can define the flow of this mesh in 2 ways. One is in this way and 1 is in this way. Okay, and you can retrieve this kind of direction by checking its principal curvature direction. The principal curvature will give you two direction values, one in this way and one in this way, based on its curvature on a surface. So by using this curvature, I'm going to retrieve this directional value and use this flow value in order to define the flow of the mesh and in order to define in which way the quad should be created, in which direction the quad should be created. Okay, so step 2 is to create principal curvature direction. Now after you have got this curvature, it's time to start creating a quad mesh from a triangle. And in order to do that, what I'm going to do is to pick the appropriate edge like these and dissolve it. By dissolving, I mean just delete it like these. And by dissolving the edge of two triangles, you'll be able to create this quad face. Now, this is when I'm going to use the information of the curvature, the principal curvature, like which edge to dissolve. So what I'm gonna do is to, first of all, let's bring this back. Oops. Let me undo this a little bit. Okay, so what I'm gonna do is to, first of all, check for each point, like each point. Okay, and then check for each neighboring primitives, like for example for this point, if I have used this point, if I'm looking at this point, then get the neighboring two primitives, in this case either this pair, or this pair, or this pair, and so on, like in an order. So first of all, I'm going to look at these pairs, okay, and calculate the direction from the center of this triangles to the center of this other triangle in the pair, which the direction will be look like these. Okay, now what I'm going to do next is to compare this direction together with this principal direction, either this one or this one. Let's say I'm going to use this one, the larger one, and using some kind using such as a dot product. Okay, so dot, so let's say this is PV, this is B1, so, and calculate dot product between the principal direction and the direction for each pairs. Okay, and do the same things for all the other pairs, like these pairs or these pairs. So it could be this direction, this direction, this direction, this direction, this direction, this direction, and this direction. Okay, and you can assume that one of the curve or one of the direction will have the largest dot product. The dot product will give you a value in between -1 to +1 if the vectors used for this dot product is a unitized vector. So what I'm going to do is to find out what's the largest, what's the one that's close to 1, which means what's the one which close to parallel to this principal direction. So in this case, the vector direction which is parallel to this direction could be either this one or this one. I mean, this is actually give you a negative value, but by making like absolute value, you will be able to have a value in between 0 to 1. So, and there's a chance that the principal curvature will just go this way, this way, this way, this way. Like, it's still the same direction, but positive negative is flipped at some point. So it might be a good idea to make it absolute as a result of the dot product, and just check its direction, not the negativity or positivity. Okay, so it could be either this one or this one will be close to 1. And let's say I found out that this direction is most close to this principal curvature's direction. Then that's when you want to make this part make this edge dissolved to make a quad. And that's for one iteration. And after doing this one, you do the same thing for all the other points until you can have until it stops by can't find any like paired triangles anymore. So do the same things for all the other edge, like deleting these edges, 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 and so on. Okay. And although there are some problems still left, because at some point there are no more like triangle pairs sticking into each other, but there's still some triangles left, the isolated triangles. Okay, so that's the next thing you want to fix. For example, if you have like a square like these, but and for the neighbor of the square you have this triangle, and have a square like these. So in this kind of situations, you have two triangles. It doesn't share its edges by as a pair, so there's no way to dissolve its edges, and it's connected to a square like these. So in this kind of cases, what I could do, what I could think of, is to add a split line in the middle of this square, and then dissolve the edge right here and right here. Okay. As a result, you'll be able to have 1, 2, 3, 4 1, 2, 3, 4 edges for each corners, and be able to have a quad faces neighboring into each other. So I'm gonna do this split operation, split and collapse operations as well to make as much quad as possible. Okay, so this is step 3, a dissolving, and step 4, split and collapse. Okay, so after doing all these steps, you still have some isolated triangles, which could be a situation like these. where the triangle is not really even not connected to any triangles, even on the edge point. So in this kind of situations, it's a bit hard to do the remesh by like split and dissolving this kind of cases. So to make it a bit more brute forcefully converted into a quad, I'm going to add a additional step to subdivide all the mesh altogether using something like a bilinear subdivisions, meaning I'm going to split all the faces to make as a quad. So in this case, I'm going to split like these for each quad, and for the triangles I'm going to add a center point and split like these. So in this, by doing this, you'll be able to have like 3 quads for triangles and 4 quads for a already quads faces. And that's the final step for making the quad faces using subdivisions. Now you might think, then it might you might say then why not just use subdivisions from the first? But if you do that, then you'll be able to have a bunch of a lot of number of like meshes or quad mesh which have like 3 neighboring quads or more than 3 neighboring quads. I'll show you what it looks like. So if you have the geometry, let's say I'll want to do the remesh for the sphere polygon, starting with this kind of a okay, so this is already triangularly remeshed. So if I try to do this subdivide, I'm going to use this open subdivide linear, which makes the quad for each triangles. If I try to do this, looks like these, which might be familiar to you if you ever use the subdivisions. Now it is still a quad faces, but as you can see, at some point you have like 1, 2, 3, 4, 5, 6 neighbored polygons, and some points you have 3 polygon neighbors, and there are no like 4 polygon neighbors in this kind of situations, and that's not really what I really want. But I want to have as much number of like 4 neighbors as possible in these situations. So this is the last dirty trick that I'm gonna use to forcefully convert the triangle into a quad. Okay, so that's kind of a reason that I bring this on the last. Okay, now after doing all these split and subdividing stuff, you still need to do something more in order to, because at some point you have kind of a deformed quad faces like these. It is a quad, but it doesn't really look like a square. It's kind of a bit deformed. So what I want to do next as a final step is to make the deformed geometry close to a square shape as much as possible as optimization. Okay, so to do this, I'm going to do a bit of how do I say the similar to what I do for the force implementation or particle-based physics simulations. I am not going to use any vellum or anything. I'm just going to do some simple simulations in order to make the face looks like a square. So to do this, the step looks like these. So first of all, let's say I have this kind of a kite-like shape. Okay, and for each point, I'm going to rotate each point like 3 times by the multiplication of 90 degrees, meaning I'm going to rotate this, first of all, 90 degrees, which in this case, I'm using the centroid of this geometry. So this first point could come something around here, and the second point could come somewhere around here by rotating 180 degrees, and by rotating 270 degrees, the point could come somewhere around here. And do the same for other points. So for this point, I'm going to rotate 90 degrees, could come somewhere around here, come around here, come around here. And for the third point, which is this one, I'm going to rotate it 90 degrees, 100 degrees, and 270 degrees. And last of all, for these points, rotate 90 degrees, 100 degrees, and 270 degrees. So by doing this kind of stuff, you'll be able to have like 4 points at each corner, like these. Okay, and after having those 4 corner points, I'm going to get the average point position of all these points. So it could be somewhere around here, 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 right? Now this cross point will going to be the goal where the corner point would want to go forward for. So I'm going to create a directional value going from the corner to this cross point. And I'm not just going to move it by this distance, but I'm going to make the distance a bit smaller so that I can slowly move the all edges close to this average. And by continually doing this, at the end, you'll be able to have a clean quad face at the end. Okay, so that's kind of a process what I'm going to use to make each quad be a square as possible, to make as square as possible. The reason why I'm using the small step for the moving each point is because each quad is facing like these. So I think it's a good idea to make it to go slower, so that each one will not affect each other that much in terms of the neighbors. Okay, so that's one of the force that I'm going to implement to make it smoothen out for the quads. Now this is not enough in order to make the quad clean as much as clean as possible, because by just having this one, you might run into situations that some of the quad remain really small in terms of area, like this. Even though it looks like squares, you might having the differences between the area. Now the center quad might be really small. The quad which connects as a neighbor might be really big. Now this is also unbalanced, so I want to fix that as well. So as an additional force, in order to move the vertices of each quad, what I'm going to do is to first of all get the average area of all the faces which is inside the geometry, get the average area. So let's say A. And you also want to calculate the area for each face as well. And you just want to calculate the differences between the average and the each area of the faces. So by just doing the subtraction, like A1 minus or AN minus A average, this will be the difference value. Okay, so if it's too big, if it's positive, then this means you want to shrink the geometry. You want to make this geometry smaller. If this negative, then that means the current area is smaller than the average, so that in that case you want to make the faces bigger. You want to expand the geometry. So looking at the negativity or positivity, you want to expand the faces in this direction or shrink the geometry in this direction inward. In this case, using the same forces for each vertices going into the center or to outward from the center, using the value of this difference as a force strength. And this thing as well might be better to make it small values, because it is all connected to each other. So by moving these points at one of the quad, it will affect the other neighboring quad. So I think it's a good idea to make the force strength small as possible. But to make it bigger, you'll be able to have a fast result, but you want to reduce the strengths as much as possible so that the simulations would not destroy the whole geometry by moving the points too fast. Okay, so that is the final step, smoothing. And that's kind of all that I'm gonna do in order to create this quick and dirty remesh. It does sound like a lot, but if you try to do a more sophisticated remeshing stuff, it's going to cost more, I think. If you look at some paper for the quad remeshing, you'll be able to see what it's like. One of the paper that you could look at for the quad remeshing, let me search for it. I think it was called as quad cover, quadrilateral cover. Okay, forgot what's that, but the thing is that there is already a bunch of plugins for Quadremesh. If you just want those results, then I think it's a good idea you just use these because what I'm gonna implement here is just a kind of experiment, just kind of a geometrical practices to understand a bit of the mesh structures. Then that's probably it. Might be not ready for production at all compared to other sophisticated plugins. So that's the reminder, and let's start implementing what I have just explained. Okay, so let's do this. So first thing first, let's prepare some geometry that I would like to remesh. I think it will be a good idea to have a bunch of different curvatures. So I'm just going to try to create some metaball geometry, or maybe I could also use sample geometry. So test geometry like pig head. Okay, I'll just use this pig head as a sample geometry. Okay, although this has already been Quadrilateral Remesh, so might not really need to do anything for these, but let's assume that you don't have this kind of information. So first of all, I'm going to delete the texture information, which is not necessary right now. Using attribute delete, I'm going to delete the texture, the material from the primitive. Okay, now I'm going to, the first step is to remesh this geometry as a triangular shape. So remesh. I'm just gonna use, this is the first step. So let's call this first step, or step 1. Triangular remesh. And this is going to be the base of the quad remesh. So it might also be a good idea if you can control the point positions for this triangular mesh, but since I'm gonna do it quick and dirty way, I'm just gonna use the result as it is. Okay. So first thing you want to define is the resolutions of the triangle remesh. Let's say somewhere around 2.5. Start with a low res. Okay. After all, I am going to use the subdivisions to retrieve the quads later, so it's going to you're going to have a bit more high res result. Meaning, if I use the subdivide, look like these. Now this one still is a bit dirty, too dirty as a quad, so I'm not gonna go straight to the subdivide. But first thing I would like to do is to calculate the principal curvature of this geometry, then use that information to dissolve the edge of the triangle using the directional information. So it's time to calculate the principal curvature. To do that, it might not be a good idea to calculate the curvature from this geometry, from this remesh geometry, because it has already been a remeshed in low res, because so the result that you get as a principal curvature might be not accurate enough. So I'm going to go back to the original geometry and use this one to estimate the principal curvature. And I'm going to make this a bit more high res by using another remesh with a bit more less number of target size. Let's say 0.1 or 0.07 and so on, so that you have enough points to calculate its principal curvatures. Okay. Now from this geometry, I am going to calculate the curvature using the measure node, and then connect it like this, and choose the curvature for each point. And for the curvature, I'm going to use this principle and change it to direction, or it could be a vector as well. The vector will give you a amount of curvatures as well, but in this case I think just having the direction is fine as a unitized direction, because I'm just going to use it for a dot product. Now you can use either smaller or larger The larger one, the smaller one will have you a bit more direction, which the point will go forward for the straightened face. The larger will give you a bit more curved direction, more and the smaller and larger is defined by a perpendicular direction. So you can, I think you can use either way. In my case, I am going to use the smaller. Okay, so that I want to use this flow to dissolve the edge. Okay, to make another as an additional process that I'm gonna what I would like to use, what I would like to do for at this point is, since the original mesh might be a bit too jaggy in some cases, which will give you kind of a jaggy curvature result as well. So in those kind of situations, I'm going to also blur this geometry a little bit so that the curvature, the result of the curvature might not be too accurate, but can be really smooth. So I'm going to use this attribute blur to blur the positions, to smoothen out the positions a little bit. And as a result, the curvature will be smoother as well. So compare with and without this smoothness, you can see that the curvature becomes a bit smoother. Now you can forcefully do the strengthen the blur by increasing this blur iterations, which will create a bit more smoother like result like these, which it could also be fine because this curvature is just going to be used as a guide which edges to dissolve. Okay, so having more blurring iterations to make the whole curvature smoother might be also be a good idea. So I'm gonna go with the 10 for now. Okay. Oh hi, Stainslav, thank you for the super chat, appreciate it. Now after having the smoother curvature value, it might not be a good idea to keep this blurred geometry result as it is, because I have to use this to refer as a reference for each of the point from this remesh geometry. And to do that, it needs to have all the points needs to be in the original position as much as possible. So after calculating this measure node or curvature, I'm going to make the point position back to the original positions by using the point wrangle. So this is the deformed geometry and this is the original geometry. So reshape, let's say reshape. And what I'm gonna do is pretty simple, just referring to the point positions from the second input, which is the original point positions. P at ptnum, and then override the current point position, which is this deformed point position, with the reference point position. That's it. And you'll be able to make the geometry back to the original positions, but keep the curvature as the one that I've calculated right here. So let's check that curvature direction. I can have a marker curvature as a vector. Okay, and let's make this wireframe. So it's a bit hard to see. But you can see that the direction but it's a bit hard to see though. Let me go back to the flat shaded. Okay, so as you can see, the result is good enough. If you want to have more smoothed out curvature you can increase these iterations and see the result. You see that more blurring value you have, you'll be able to smoothen out the curvature as much as possible. Now let's keep it as 10 for now. Okay. And I'm gonna make this back to a smooth with shaded. Okay, so now that I have this reference information, what I'm gonna do next is to use this one to decide which edge I should dissolve for this triangular meshes. Okay, and I have to do one by one iteratively. If I do it for 1 point neighbors, then by deciding which edge to dissolve, I have to dissolve it first, then go to the next point to calculate the other points. Okay, and probably the order of which points to pick next might be important, but I'm gonna do it randomly this time to make it, as I said, quick and dirty. So first thing I'm going to do is to use the sort to randomize the point order so that I can pick up the point randomly. So make this random, these. Okay, now to pick up the point iteratively one by one after doing the dissolving, the easiest way I could think of is to use the for each feedback loop. So I'm going to use this for each number to do that. I'm going to set the for loop to a feedback age iterations for each end, and fetch feedback as a for each begin, which will create a feedback loop node. Okay, and in between then I'm going to create a node to get one of the random points, and then get the neighbor polygons for that from that point. Let's say I'm going to pick this point and get all the primitives, and then get the pairs, to get the neighboring pairs from those polygons, and calculate the direction from the center of the triangles to the neighboring triangles, and use this direction with the referenced principal curvature from this geometry to calculate the dot product. And if the dot product is the largest, then that's the edge, that's the pairs that I want to dissolve. And then after deciding which edge to dissolve, I'm going to use a node like dissolve node to dissolve that edge. And that's for the one loop, and I'm going to continue doing that iteratively again and again until you don't have any triangle pairs anymore. Okay, so let's try to do that. Okay, I am going to use a and I think it's a good idea. It still is a random. The point order is still random, but I think it's a good idea to start from the point which has the largest number of neighbors, because I want to reduce the number of neighbors as much as possible until it becomes 4. Okay, so thinking like that, I can first calculate the neighbor count for each point by using like point wrangle. Let's name this n count, and let's calculate the neighbor count by and apply to an attribute of each point as an n count. Calculate the neighbor count at pt num. All right. Now look at the geometry spreadsheet. You have like from 4 to 9, okay? So what I'm going to do here is to start from the point which has the largest number of neighbor count, like 9. If you have a so many number of neighbors, then by dissolving one of the pairs, you'll be able to decrease the neighbor count into, in this case, 9 minus 1 and becomes 8. Okay, so making as much number of 4 neighbors as much as possible is a good idea. So I would like to start by the dissolving from which has the largest number of neighbor count. Okay, so that's kind of idea. So after getting the neighbor count, I'm going to reorder the point again using the sort. So I might not need to do this sort after all, but just in case. I don't know how it works in Houdini when you do the like 2 different kind of sort together. I'm not sure if this sorting will use the result from the previous order, or just redo the stuff all over again. If it does, then might not be really necessary, but just in case. Okay, so for the point sort, I'm going to use the attribute and count, which is the neighbor count that I've just created, and make it reverse point sort so that it will start from the largest neighbor count. That's like this. So starting from 9 and at 4. Okay. That's good. Now's the time to actually do the dissolving part. Now you can you can do the dissolving directly inside the like wrangles, but instead of doing that, I'm going to use the dissolve. So in order to use the dissolve node, you have to define which edge to dissolve by defining as a group. Okay, in this case, you have to define the edge group right here. So what I'm going to do is to create some wrangle, like an attribute wrangle, to look for each point, and then dissolve one of the edge and make these edge as a dissolving group, and use this dissolve node to dissolve that edge, and finally you'll be able to have a result and first result, and then go back to the first step and do the same step over and over again until you have no triangle pairs. So let's name this group as dissolve edge group. Currently I don't have any dissolve edge group, so it gives you an error. It's not a problem. Okay, and for this attribute wrangle, let's name this choose dissolve edge. And to choose, I need to access the principal curvature information, so I'm going to connect this geometry that I've created with a curvature a attribute to the second input of this attribute wrangle. And for this attribute wrangle, I am going to change this to a detail, because I don't want to simultaneously access to each point, because that will mess up the calculations. You don't want to simultaneously parallelly calculate for each point, but you just want to go 1 point at a time. Okay, so for that reason, I'm going to set it as a detail. Right, so it's time to write some first step of a code. See what I need to do for that. Okay, so first of all, I am going to create a loop accessing to, let me open up the editor. Okay, first of all, I'm going to loop all the points, loop through all the points on the geometry using endpoints. Endpoints is the total number of this mesh, right? And in this case, I will be the number of the point number. Okay. Now, next thing I would like to do is to get the neighbor information at each point. So int neighbor point list using neighbors. Okay. And thing is that I don't really need to do the remeshing, or I don't really need to dissolve the edge if the length of the neighbor is less than 3. If it's less than 3, if it's less than equal than 3, then you don't really want to dissolve the mesh. Otherwise, you're going to, the situations that what I'm talking about is something like look like these. So let's say you have square, you have square, and you have triangle, or maybe a bit more other situations. You have one square, and you have for this point, and you have 2 triangles like these. Okay, this is the situations that I'm talking about, and this triangle is connected as at the edge as a neighbor. So you could dissolve this edge to make it as a quad, but you don't really want to do that, because by doing it you are having 2 quad sharing the 2 edge at the same time, like these, which will give you a bit of problem in terms of the mesh structures. You'll be able to have, you are going to have a bit of problem right here rendering it. So if it's less than or equal to 3, then you want to keep, even though if there's a triangle geometry, you don't want to dissolve this kind of stuff. You want to keep it as a triangles and leave it to a subdivisions to make it a quad. So doing like these instead of dissolving it. Okay, so that's one small rule here. Okay, saying, okay, sorry, my thumbnail is blocking the code. Sorry for that. So this is what I've been writing for. I'm using the for loop to accessing each points and get the neighbors list point using the neighbors function, then checking if the neighbor has less than or equal to 3. Okay, if it's less than or equal to 3, then that's not the point that I want to use for the dissolving, so I'm going to skip this by saying return, or continue, probably continue, go to the next point. Okay, hello everybody. Okay, now let's try to then get the all the neighboring points, or all the neighboring like primitives at each point. Okay, so to do that, let me think. That's the best way. So first of all, I'm going to define the max dot product value starting from 0. Because I'm going to use the absolute value, the minimum value of the dot product will be equal to 0. Okay, And then I'm also going to retrieve the curvature at the point position from the second input. Okay, to do that, you can, I'm going to name it as curve. So using the point functions access to the second input, the name of the attribute that I want to access is the curvature. And actually, no, this is not the right way to do it. But actually what I want to do is to first of all, get the current point position at I iteration when the iteration is equal to I. So vector point position pt pass is equal to 0.0 p at I. So this is the current point position for each iterations. Could be somewhere around here, could be somewhere around here, starting from the neighbor equal to 9 in this case. And using this point positions, I'm going to sample the curvature from the second input, which is this one. So to do that, you can use the function called UV sample from the second input. The attribute that I want to sample is curvature, and the UV value that I want to use to sample is point position, and the actual point position that I want to use for the sampling is PT pass that I've just retrieved. Now by doing this, you'll be able to get the closest curvature value at each of the point from this reference geometry. Right. Now that I have this point position, I am going to get the neighbor point from each of the neighbors list that I have retrieved right here, to see which edge, which pairs of the triangles have the largest dot product. The close to the principal direction in terms of its center to center direction. So I'm going to create another for loop, and let me change the first I value to t. Doesn't really make any changes, but just in case, and the sample that I had created previously, I name this as t, so that I don't get confused too much. Okay, so I'm going to create another for loop. In this case, I'm going to use I as an iteration value, and the number of iterations that I'm going to do for this loop is the number of neighbors. So for each neighbors, I'm going to create the calculations. So let's say I'm looking at this point and looking at each of the point, using the number of neighbor points for this point as a loop iteration number. And let's say this is the first iterations. This is the first neighbor points. What I'm going to do is to use the half edge structures to get the neighbor of this edge from on the right side and the left side. Okay, and if these are triangles, I'm going to retrieve the direction connecting the center of each triangles and calculate the dot product and see if it's bigger than the current maximum dot product. If it is, then update the max product, and hopefully that will be the one that I want to solve. So let's see. So retrieve the neighbor information, neighbor point numbers, and then as I said, I want to use the half edge to retrieve the primitive at the right side and the left side. So I'm going to get the half edge information first. So let's say I'm going to name the first half edge informations going from the original point to the neighbor as a previous half edge, and from the neighbor to the starting point be as a next half edge, or half edge 1 or half edge 2, either way. So P half edge is the half edge informations going from using the point edge function at the 0 connections, 0 geometry informations. So T is the first point, which is equal to this one, which is the current point number, and the neighbor is the neighboring point number, which is this one, if you are looking at this one as a T. So this is T, this is ney. Okay, so this is the first half edge. The second half edge you want to get is the point edge neighboring point to a current point position, current point number. So just make these reversed. Okay. So from each of the half edge you'll be able to retrieve the primitive number as well. So that's what you want to do next. Okay, now but before doing that, you might also want to check the other stuff as well. Look using the neighbor point, like for example, in this case, this is the current point and this is the neighbor point. Okay, at the neighbor point, you also want to retrieve the number of primitives which is attached to this neighbors. Okay, and you want to check if the neighbor point, if the neighbor primitive, let's say what I'm gonna do. So wait a minute. That was too fast. Okay, so forget about that, and first thing I want to do is to get the primitive number out of these half edges. So let's name the first primitive number as p prim. So hedge, using the hedge prim function, and for the next primitive I'm going to use the same function and hedge. Okay, so by doing this you'll be able to get the primitive number for this one and this one. If it's starting point to the end point, the neighbor point, using this as a half edge, you'll be able to get, I think, this primitive, or this primitive, I forgot which one. I think it was in clockwise order, probably. So probably this one. And for the half edge going from this one to this one, then you'll be able to get this primitive out of this hedge primitive. Okay, now that you have two primitives, you can get the center point for each point, from each triangle primitive, and calculate the direction. But to do that, you have to make sure that these neighboring primitives are triangular. Okay, meaning you have 3 vertices. There is a chance that you getting the quad face as well. In those cases, you want to skip that face to calculate, because you don't want to dissolve that edge. So you want to calculate the lengths of the prim points to retrieve the number of edges or number of vertices it has for each primitive. So the lengths of prim points will give you a number of vertices for each primitive, in this case a primitive, and if it's equal to 3, and the lengths of prim points 0 next primitive is also equal to 3, then that's the condition you want to do you want to calculate the dot product. Okay, I think I'm getting the error. Let's see where that is. Okay. 18 primitive. Is this what I'm doing wrong? Nope. Is this what I'm doing wrong? Yup. Okay, so let's see what I did wrong here. So int p prim hedge prim doesn't look wrong, but it is. Let's see why. Enable to load shared shader 18 reference to undefined variable p hedge. Okay, spell mistake. All right. Typos. Okay. So if the neighboring primitives is triangular with these conditions, then that's when you want to calculate the direction going from one of the center to the other center. So let's get the center position for each primitive. Vector pos is equal to prim 0 p prim, which will give you a centroid of the primitive. Next one, and pos prim 0 p and prim, the other centroid. Now you can calculate the direction going from one of the point to the other point. Let's also normalize this, and pos minus p pos. All right. Now, after doing this, you can now calculate the dot product between the curvature that you have retrieved right here. So float dot val is equal to a dot between the direction and the curvature. And you want to make sure you are getting the absolute value, because it could be like a reverse direction, 180 degrees reversed. So to make sure that I'm just looking at its direction without its positivity or negativity, I'm just going to make it positive and just want to retrieve the largest value, the largest absolute value as much as possible. So if this dot value is bigger than the max dot, then I want to update the max dot product to the current dot value. And I also want to retrieve the current point number that I have retrieved and the current neighbor point as a target point, so that I can get 2 points to see which edge is the largest, which edge should be dissolved. So I do need to have a variable which stores that information. So I'm gonna go outside the loop and create 2 integer parameters, integer variables. One is pick source, starting with -1, and pick destination, starting with the negative. Okay, and going back here, if you have found out that the current dot value is larger than the current max dot, then the max dot will be updated, and also the pick source and pick destination is also be updated. In this case, the pick source will be updated with the t, which is the current point number, which is this one, and the pick destination is updated with the current neighbor information, which is nay. So like this. All right. Okay, so and this is all good, I think. And as soon as you found out, as soon as the pick source or pick destination has been found out in this loop, then you don't want to, you can just leave the loop as soon as possible, as soon as this has been updated. You do want to do all the iteration, you do want to operate for this loop until it ends, because it's just looking at all the neighbors at one of the point. But after you have found any point can be used for the dissolving, then that's when you want to leave this whole loop. In this the parent loop, you are looking at each point from the largest number of neighboring number to the lowest. So after leaving this loop, the child loop, I'm going to check if the pick source has been updated. If it's more than 0, then that means some number has been applied other than -1. So that's when you want to leave this whole loop. So I'm just gonna say break. Okay. Now that I have left all those loops, it's time to set the edge group to say that that's the edge that I want to dissolve, which connects with this source number and the destination number. So if the pick source is more than 0, more than or equal to 0, then set edge group. Then the name of the edge group that I want to apply is dissolve, and connecting pick source point number to the pick destination point number as 1. Okay. Apply. And you probably want to define when to stop this whole loop, this for each loop as well. And to do that, you can define when to stop by checking if the current pick source is negative. If it's negative, that means no pick source has been chosen, even though I have looked through all the points. Okay, meaning you couldn't found any like triangular pairs in this situations. Meaning there are no more loops you need to go for. There are no more dissolving steps you need to go for. So that's the time when you want to stop the whole feedback loop. So in that case, I'm going to set the detail attribute. Since we are in the detail attribute, I can say I at stop to 1. Okay. I gotta use this with inside this stop conditions later, but for now, let's leave that. And going back to this add dissolve, and one of the edge must have been dissolved, and you can see that I'm gonna stop by setting this the iterations equal to 1, and let's see which edge has been dissolved. It's a bit hard to see, but one of the edge must have been dissolved, and you probably this one right here. Okay, and let's also check go back to this reshape and check its curvature and if it's doing what it does. So by looking at this curvature, I can see that the flow is going somewhere in this direction, somewhere around here. Okay, so this is the direction that we're looking at. And using this curvature, I have just resolved one of the edge right here. And this is if you try to get the direction from the center of this triangles to the center of this neighboring triangles, you could kind of see that its direction is pretty similar to its principal curvature. Curvature direction. So that's the reason why this edge has been chosen to dissolve. For for this direction, it's a bit far off. Maybe this is pretty close, but for the other direction is a bit too far off. Now this was the closest edge. This was the closest direction, so that's the reason why this edge has been chosen to dissolve. Okay, so that was for the first loop, and by increasing the loop iterations, you are looking more and more edges until it no longer finds out the triangle pairs. So I'm gonna increase the iterations to, let's say, 100. Start to see more dissolved edges. Maybe you can increase more, like 1,000. And now you see probably you don't really have any triangle pairs anymore, like these. Okay, looks good. Now you can make this number as much bigger as possible, but which will create the calculation times also bigger. So that's when you want to use the stop conditions to stop as soon as you don't find any triangle pairs anymore. So if the detail attribute has the stop integer stop attribute, then if it's equal to 1, then that's the timing when you want to stop this loop. So I'm going to create the new node at the starting point. Let's name this state. Okay, I'm gonna check the detail attribute of this state, and if you have the condition attribute called stop and it's equal to 1, then that's the timing when you want to stop this feedback loop. So going into the stop conditions, I'm going to refer to that attribute, detail attribute. So I'm using expressions, detail, state, and stop at 0 index. If it's equal to 1, then that's when you want to stop. And as you can see, by doing that, you'll be able to reduce the number of feedback loop like these. So the maximum number in this case is 212. So in that case, you can increase this iterations as much as possible, but still be reduced to a minimum number. All right, that's good. So I'm gonna keep this iterations to 10,000, but still the feedback loop end at 200. Right, now let's try to change the smoothness of the curvature and see the difference, what it creates. If I set the blurring iterations to 0, then you start to see a bit more randomish dissolving result. It still use the original like curvature, so it does refer to a curvature. It still does referring to the curvature, but the result you get could be a bit more randomized in terms of the direction. If you make this like 20, the direction might becomes a bit more smoother in terms of the flow. Probably. I'm gonna keep it to maybe 15. Okay, so that's that. And there is one condition I didn't apply for this dissolving edge, so I would like to add that as well. And I gotta remember what was the condition to use that. So let me save this first and open up the editor. Okay, so there is some situations that I want to skip calculating the dot product. And let me think what was that conditions about. Okay, so I'm going to go to the sketch here. And okay, I'm checking out the samples right now, and so the point has several neighbors like these, and this is the T, this is the N. I'm just gonna call N, right? And if the neighbor primitive have something like three neighbors, three primitive neighbors, meaning could be situations like these. Okay, in that case, you might not want to dissolve this edge, because that will give you, by dissolving this one, you're having this kind of situations. Same as the same reasons as previously. The one triangle is sharing two edge from the quads, which will give you a kind of a irregular mesh, which you don't really want. So in those cases, you don't want to dissolve it. You want to skip dissolving that. So let's add that condition. Okay, so going back to the code. So probably that could be somewhere somewhere around here. Okay. And okay, probably I also want to add another conditions as well. The case what I was talking about is when the point is at the center of the mesh. Okay, so but there is a situations that you are looking at the naked edge of the mesh. Or I mean the unshared edge of the mesh. So let's say this is the mesh we are talking about. And this is the unshared edge, meaning there are no connection in this side. It's empty. It's we call this unshared edge or naked edge. Okay, in those cases, the neighbor of this point is either this one, or this one, or this one. Okay. And there is a chance that if you look at this point as a neighbor, like this is a T and this is a neighbor, and previously we are getting the two half edge values, one for these, one for these, one for this direction, one for this other direction, and to retrieve the two primitives, two neighboring primitives. But in this case, there are no like neighboring primitives available in this case. So as a result, what you get as a half edge information, like if you try to get the half edge going from T to N, you get a half edge value, let's say equal to A. And if you try to get the half edge from N to T, you get the same half edge information called A, if you don't have any like neighboring primitive. So that's a problem, because this gives you the same number, so which will, if you try to get the primitive number out of these half edge, you get the same triangle geometry, triangle primitive, and if you try to get the directions, then you get 0. And you not be able to calculate the dot product using those values. So that's also the condition when you want to skip calculating the dot product. So there are two conditions you want to skip. First of all, the first conditions, if the neighbor point has a 3 primitive, then you want to skip that. So if a length of, first of all, let's get the neighbor primitive, neighbor primitive, the neighbor primitives of the neighbor point. It's a bit confusing. So nay prims is equal to point prims 0 neighbor. And if the length of the prims is equal to 3, and as well as the current, as well as if this neighbor primitives include this primitive number right here, or the primitive number right here. If that's the situations, then that's when you want to skip calculating. So find prims n prim is larger than 0, and find prims p prim larger than or equal to 0. Okay, then that's the situations. You want to skip these iterations and go to the next one. All right, so that's one situations. And another situations is if the p hedge, the half edge 1 and half edge 2 is equal, then that's also the situations you want to skip. So n edge. Then also continue. Okay, let's apply. In this kind of a small sample, you might not get into that kind of situations that much, but just let's make sure that we cover everything we need. So I think this is fine. Let's accept. And this is the step 2, dissolving. Takes a bit of time, but worth it. Step 2, dissolve. Now what was the step 3? Now step 3 is to get one of the situations. You could convert the triangles into quad. For example, in this samples, one of the situations that I'm talking about is kind of this one. So triangle, you have two triangles sharing the same vertex, and it is connected to the same quad mesh. Okay, so this three pairs, two triangles and one quad pair can be converted into two quads by adding a split line on the center of this quad, then dissolve the edge right here and right here. Then as a result, you'll be able to have the two quads from these informations. Okay, so that is to make as much quad face as much as possible before getting into the subdivisions. This one as well, you can retrieve these pairs and then add the split line either this way or this way, and then dissolve the edge to get two quads. Okay, so that's what I would like to do here. Let's see how we could do that. Okay, so first thing first, let me reset some of the attribute that I have set. Something like a detail attribute like stop. So I'm going to do like attribute delete unnecessary attributes. So for detail, stop. For the other one, probably don't need the texture. UV in count positions, probably these end count is no more appropriate, so I'll also going to delete that. Okay, so clean the attributes up and let's try to do this. Now for this one as well, I do have to do one by one and find out the propagate pairs where I want to add the split line and dissolve. So like I did last time, I'm going to use another for each loop. Okay, pretty similar to this. Is not going to take that much of a time in terms of the calculation, but the things that I'm going to do is pretty similar. So feedback loop, fetch feedback. Okay, starting with the 10, I think it's good. Now, like we did last time with this one, in order to stop, I'm going to create another null node. Let's call this state 2. And let's also sort it out the primitive again. And to do that, I would like to recount the neighbor count, so that I still want to dissolve where the point has the largest neighbor count. I think by doing this first feedback loop, I have reduced the number of neighbors, but there are still like neighbors available which has a lot of neighbor count, like these, like 1, 2, 3, 4, 5, and so on, more than 4. So I'm going to start with these. I'm going to check with these points which have more than 4 neighbors. So to do that, pretty much I'm doing the same things. I'm first going to calculate the neighbor counts. I'm going to copy this one, apply it here, and check the geometry spreadsheet for those points. So currently the maximum neighbor count is just equal to 6. Okay. So I also want to sort it out based on those n count. So I'm going to do another sort node for the point to sort out based on the n count. And there you go. Going from 6 to 3. All right. Now, next thing. Now that I have those value, what I'm going to do is to create another detail attribute. Okay. Attribute wrangle. Make this as a detail. And well, what was I doing? Split collapse. Okay. And this is going to be the step 3. So let's try that. So like we did last time, I'm going to loop through all the points first using the loop through all the points. Let me open up the code editor again. Okay. So for int I 0 and points, so previously I was using t as an iteration number. Currently I'm using I because in the sample I use I. That's the only reason. Okay, I'm also going to create a number called pt. Just replace with the I. Just copy the I value, which it's not that necessary, but just to make sure I know that this I value is related to the point to have less human errors. Okay, now I'm going to get the neighbors out of all the points. at each point. So currently, if I'm looking at this point, I'm going to retrieve all the neighbor points again. So int neighbors list is equal to neighbors 0 at pt. Okay, and the number the conditions where I want to look at currently is where the number of neighbors equal to or more than 4. Okay, if it's 3, then you don't want to dissolve and collapse anymore. So if the length of the neighbors is more than 4, more than or equal to 4, you could say more than or equal or just more than 4. You could skip the number 4 if the if the neighbor point number is equal to 4, then you might also want to skip that as well. Situations like these, you have a I mean, this is the situations that I'm talking about, but let's see if there's the conditions what I want to talk about. Not really. I don't see it. I don't see much. Okay, maybe. Well, you can maybe I'll show what's the difference between going into equal or more than 4 or just more than 4. I'm gonna go with the more than 4. Okay. Now, first thing I would like to do is to access all the neighbors. I want to look at, let's say I'm looking at these. So this is when you have 2 triangles sharing the same points and you have 4 neighbors. So in this kind of conditions, this point will going to be skipped. So this quad is not going to be split into 2, and this is not going to be converted into 2 mesh. The reason why I'm skipping right here is because by doing that, you are having 3 quad neighbors at this point. But the result that I want is actually having 4 quad neighbors. So that's kind of a reason why I'm skipping this one. But since it still is a triangle, even though you have 4 neighbors, so it might also be okay you splitting this into 3 quads based on some situations, but I didn't really go that far to see if that's good or bad. So I'm gonna go with more than 4 for now, and this could be a situations that could match with these situations. So you have these 2 triangles, 1 quad right here, and you have 5 neighbors. So this can be this situations could be the one that I would like to do the remesh. So, and this is actually not like triangles, but this is actually a quad because you have 4 points. All right. So after having this kind of situations, I'm going to loop through all the neighbor points using another loop, and length of neighbors. Okay, and get the neighbor value, neighbor point information. Now, I am still going to get the half edge informations, okay, at one of the points. So let's say by looking at this point currently as a PT, the first neighbor point, let's say this is the first neighbor point right here. And what I would like to do is to get the half edge information going from this center point to the neighbor point. So int edge is equal to point edge 0 pt neighbor. Okay. And you can actually get the equivalent half edge going from the neighbor to the center. Previously I was using like point edge from neighbor to pt, but there's other way to retrieve the same things. That is to use function called edge next equivalent. So equiv edge 1 is equal to edge next equivalent 0 at edge, which is similar to what we did getting the half edge from the neighbor to the pt. Okay, doesn't really matter which one you use. All right, now the next thing I would like to do is to, since I want to get the conditions where I have first triangle and then have quads and then the next one becomes triangle. So what I'm doing here is first of all, get the half edge going from this point to, let's say, let me think what I did. So first of all, I think I have retrieved this half edge right here. Then go to the next half edge, which is from this point to this point. Okay. And the next thing I'm doing here is to try to retrieve the next neighboring edge. So to do that, the good idea is to first get the half edge going from this point to this point, then use the equivalent half edge going from this point to this point, which belongs to this primitive. Okay, then by using another half edge function called edge half edge next, you'll be able to get the clockwise half edge next directions. So if you for this primitive, if you're going from this point to this point, then the next half edge you can get is this point to this point. Okay, then by using another equivalent half edge equivalent functions, you'll be able to get the half edge going from this point to this point for this triangle mesh. Okay, and using the same half edge next, you'll be able to get the half edge from this point to this point, which is on top of this primitive. So as a result, you'll be able to get 3 edge informations. Okay, by having those 3-point informations, you'll be able to estimate whether those each of the primitive has the met conditions 3, 4, 3, or 3, 3, 3, or 3, 4, 4, and so on. If the primitive vertices number is equal to 3, 4, 3, then that's the situations you want to do the split and dissolve. And that's kind of reason why I'm using half edge to find out those situations. Okay, I hope it makes sense. If I write in the sketch, and let's see. So, starting from the first half edge, let's say H1, okay? Then, which belongs to this triangle right here. Then using the half edge equivalent, you'll be able to get this other side half edge. Let's call this half edge 1 dash. or quote. Okay, and then by using this one, by using the next half edge function, you'll be able to get the clockwise directional half edge one by one. So the next one will be this half edge 2 inside this primitive. Okay, and by using this half edge 2, you'll be able to get another equivalent half edge for this next triangle. Let's call this half edge 2 quote. And this from this half edge 2 quote, you'll be able to get the next half edge, which inside this triangle mesh, which is half edge 3. Okay, as a result, you'll be able to have this 3 types of half edge which belongs to different primitives but neighbor to each other, adhere to each other, like these. So by using those half edge, you'll be able to get the primitive numbers P1, P2, and P3, and you also be able to get the number of like vertices for those primitive. This is equal to 3, this is equal to 4, this is equal to 3. And if it's 3, 4, 3, and that's the situations, you want to add the split line and dissolve those lines connecting triangles and quads. And as a result, you'll be able to get 2 quads. 1 and 2. Okay. Which might not sound like easy, but that's the things that I'm going to do. So probably this is one of the good example using half edge. Like, what's the half edge for? Many people ask me why you use half edge, but when you're dealing with the meshes, it's pretty important mesh structures. Like in this kind of situations, when you want to do the analytical like process. So let's see. So this is the first equivalent half edge value, and let's name this half edge 1. Okay. And the next thing that I would like to get is the half edge 2, which is the next half edge of this equivalent half edge. So to get that, you can use the function called hedge next for this equivalent half edge 1, which belongs to these one belongs to the second primitive. This one belongs to the first primitive. Now do the same for the third one. Int equiv half edge 2 is equal to half edge next equiv 0. Gotta go with this one. Hedge 2 and int hedge 3 hedge next 0 equiv hedge 2. That's like that. So now I have just retrieved 3 half edges belongs to different primitive and adhere to each other. Hedge 1, hedge 2, and hedge 3. Right. Now it's time to retrieve the primitive numbers out of these half edges. So let's do that. Prim 1 is equal to hedge prim 0. Okay, I'm getting hungry or thirsty. I don't have any water right here. Okay, and do the same for primitive 2 to primitive 3 for half edge 2 and half edge 3. Okay. Now I also want to get the vertices numbers for each primitive. So int pt count 1 is equal to a length of prim points at prim 1 do the same for the primitive 2 and primitive 3. Okay. Now, the condition where we want to get at the split line is if the PT count 1 is equal to 3 and PT count 2 is equal to 4 and PT count 3 is equal to 3, 3, 4, 3. Alright, now let's do this. So after we have retrieved the point informations, we need to, in order to split, I think there is a node to split the geometry in Houdini as well, but it's a bit hard to use something like polysplit. In order to use this polysplit node, you have to have a additional node to, such as like curves. And I'm not sure what kind of types you can set as a split locations, maybe a point number. If that's so, might be easier to do. Let me test this out. If I have a grid 2 by 2, okay, and you have 0, 1, 2, 3. So let's say I want to create the split line from the point number 1 to point number 2. See how I can do that. If I can do that with these. Nope. Can this, maybe this split location doesn't really allow you to enter any point numbers, but you might have to define the curve like a line geometry. What's this? Split from this point to this point, enter. Okay, so it says, seems like you have to define the vertices numbers to use this polysplit. And I'm not sure if you can use a if you can use the, what was I trying to say? If you can use the attribute. There is one called edge group. So maybe this can be used, edge group. Let me see. I haven't really used this node that much, so gotta try this out. Just gonna use the detail and let's say set edge group connecting, let me say split connecting 1 and 2. But this is not really an edge, so might not work. Okay, so didn't really work. So instead of using this node, I am going to like recreate the mesh, recreate two meshes out of the two triangles. So where was I looking at? So this one. So meaning I am going to create 1, 2, 3, 4 quad right here and 1, 2, 3, 4 quad right here, and delete those triangles and quads right here. So deleting those 3 primitives and add those 4 vertices mesh procedurally using Vex. That's what I'm gonna do here. Alright. Instead of using polysplit node, which might be straightforward and might be a good idea. Alright, so let's see what I need to do. What I need to do is to retrieve those point informations in order to create those primitive that I need. So let's see. First thing first, I would need to retrieve all those target points, which is in this case, so this is going to be the first point. This is the first point. This is the destination, which comes from the neighbors. Okay, and this is the, what was it? The what was it? The H2, the goal of the H2. So you can also get that. This is the goal of the H3, and what we are missing is this point right here and this point right here. Okay, so let's try to retrieve that. All right. Oops. So first thing first, I'm going to get the missing points, which is the point number of this half H2 and half H3. Right. So I'm probably for the half H1 as well. So meaning I'll be able to get 3 target points. So int destination 1, a H this DST point, which will give you a destination point from the half H1. Do the same for 2 and 3. 2 and 3. All right. Now, I'm also going to retrieve the oh, what was I trying to do? I'm also going to retrieve the primitive points out of the first primitive, which is this one right here. So, which is going to be this triangle right here. Is it? Oh, no. No, actually, I want to get this point for this quad. So I should use this primitive, which is equal to primitive 2. And out of this primitive, I want to retrieve this point number. So first of all, I'm going to get the p point number array from this primitive 2, prim pts 2 is equal to prim points 0 at prim 2. Okay. And just want to retrieve this point. So to do that, the easiest way I could think of, I mean, there are probably several ways you could think of. Like one of the way is to use the half H2, and by using the another edge next, you'll be able to get this half edge right here, going from this point to this point, and get the destination point of this next half edge, and you'll be able to get this point. So maybe that's much clever. So let's do that. Half edge 2, 2, 2, 1, 2. Just stay 2, 2, or 2 diagonal is equal to half edge next 0 edge 2. Okay, and you'll be able to get this point number. How do I call this? Destination 4 is edge DST point 0 edge 2D, or destination 2D. I don't mean by two-dimensional, I mean by 2 diagonal. Okay. All right. So, do I have enough information? Do we? I think I'm still missing this point right here, which I'm not sure if I have retrieved somewhere. Not sure. Not really sure, maybe not. So let's also retrieve this one as well. You can get that the same way I did for this thing here. So which can be a half edge next. You can use the same half edge next functions for this half edge right here, which is the half edge 1. Okay, so the next half edge for this half edge is it's going to be this one, this direction, and by getting the destination point you'll be able to get this point right here. Also let's call that destination 0 int dst0. First of all, I'm going to get the half edge, so half edge 1d is equal to half edge next 0 half edge 1, and then get the destination. I'll just go 1d and edge dst point 0 half edge 1d. Alright. Okay, now I think I have enough point informations to create 2 quads. One for these, one for these. So let's try this out. So I'm going to create a primitive new prim1, new quad 1, add prim 0 poly. Now I think it has to be counterclockwise or clockwise. I forgot which direction. Let's try this out from clockwise. So looking at these ones, so this is the first point, which is equivalent to I or PT. So PT comes first. The next point, let's start with these right hand side here. And so the this point right here is destination 2D. So DST 2D, and this point right here is DST1. This one, DST1, and this one right here is DST1D. DST1D. Okay, so that's one quad. Another quad, new quad 2 is equal to add prim 0 poly, starting with the same number PT. And this way I'm going to connect from this direction. So this one right here is DST3. So DST3, and then comes this one, which is equal to DST2. Was it DST1? Okay, I think so. DST2. And finally comes right here, which is DST2D. So DST2D. Okay, apply. And something has been changed, I think. Let's limit the number to 1 for now, so that I can see clearly where has been changed. Okay, seems like this right here has been changed somehow. Is that the situations that we wanted? Now we also want to delete the unnecessary primitive. So if I am adding these primitive, then I should remove this 2 triangles and this quad. So let's see, I can do it somewhere around here probably. So if no, just say remove prim 0. So in order to get the primitive number, I think I already did these one. Okay, so remove prim 1, do the same for all these. And after I have removed the primitive, I can just leave the first loop, the feedback loop at this time. So I can just leave all the functions by saying return. Okay, that's probably it. And let's see what else I need to do. In some situations, I might want to skip dividing those quads. Maybe this could be one of the situations when you see these quads, and if you create a split line right here, you see that it's getting really long triangular face or really long edge, diagonal edge right here. Might not be, in that case, it might not be really a good idea to add the edge in this direction, but might be a good idea to add in this direction, which will still create a triangle, but can keep the length for each edge as same as much as possible. Okay. So, but in that case, you might need to add another 2 quads right here, which might be a lot of work to do. So I'm I'm just going to skip splitting the edge when comparing the diagonal lengths from this edge and this edge, and if the edge that I'm trying to split is longer than the other diagonal edge, then I'm just going to skip those, want to be splitted. Okay, you can add your original like custom implementation to make a bit more smarter, but in this case, in my case, I'm just going to skip. So to do that, I need to get the distance between these diagonal points and these diagonal points. So let's do that first. Float this one is equal to, so I already have the enough point numbers, so I just need to get the point positions. So from this to this, from this one is the PT, so vector pos1 is equal to point P at PT, vector pos2, which is this one right here, is coming from the destination 1, this one right here. So I'm gonna copy this one right here, this DST1. Okay, another one, vector pos3. For this point, this is equivalent to a hedge 2D or destination 2D, so DST 2D, and the last point positions for this quad right here is equivalent to DST2. Right, now I can calculate the 2 diagonal distance. First, let's get the distance between this point to this point where I want to create a split line. So distance between the current position 1 to position 3, and the other direction, distance between the position 2 to position 4. Now compare those two, and if the distance 1 is smaller than the diagonal distance, then that's when I want to split. So if this one is smaller than distance 2, then do the split. Alright, and then as soon as it has created the split, just leave this whole loop, this whole function, then go to the next feedback loop to find out the next split positions. Right? So apply next and see if it's working. Not sure which one has been splitted at this moment because it's 0. So if I increase, you start to see some changes right here. So let's see. Okay, so I see something happening here, so let's check this out. Okay, so this is the previous situations. This is the next situations. So in this case, what has been changed? Okay, so you are having the quads on the center right here connected to this point, and you have 2 triangles connected to this quad, and you can see that has been converted into 2 quads like these. Okay, like these. This is just a small step, but I think it's useful to make this whole mesh a bit cleaner. You start to see these changes right here as well. So this one, you have triangle, and quad right here, and converting this to 2 quads like these. Working great. All right. So continue doing that until it no longer find any like split like we did last time for the for each loop. So going back, I'm going to create a stop condition when this things should stop. Okay. Now, so if you could go through all the loop with this one, which means this didn't have any like split conditions anymore. So I can just say set for I at stop equal to 1 without using any conditions, because if this can go through, then which means you couldn't find any split positions, right? So stop equal to 1, and that's when you want to stop this feedback loop. Going back to the for each and checking the detail attribute of this state 2 node. Detail state 2 stop. Okay, we're almost there for the hard coding part. Not 1 but 0. Okay, so let's check this out. Let's increase the iterations to 100, and it stops at 9, so I think the stop conditions is working. Perfect. All right. Now we are almost there. Now we have done as much things as we could in order to convert the triangles into a quad. Well, as you can see, we still have a bit of triangular meshes left out, like these isolated triangles. Probably there are like other ways to collapse and split to make all those quads without using like subdivisions, but since this is a quick and dirty way to make it quads, what I'm gonna do, finally, I'm going to use this subdivide node. Now I'm gonna say this is the step 3. Step 3, a split and collapse. All right, so step 4, which is easy, just subdivide using a open subdiv by linear. Keep the edge point position as it is. And as you can see, the result of the mesh you get is, in terms of the quad, it's looks better than the original like subdiv result. If you don't if you don't dissolve any edges for the triangles, just directly connecting the result, the triangulated geometry to a subdivide, you get something like this. But by doing all those operations with the feedback loop, you'll be able to get a bit more flow quad result, and that's good. Now you do see some kind of meshes like these, which comes from the isolated triangles, but we're just gonna go with these for now. All right, now it looks good, but it's not really that clean at all yet because it's too like squared, too pointy, and the shape of the quad doesn't really look like a square. So the final step, or almost the final step, is the one to smoothen out these faces so that it will have the same length of the edge for each quad, and then also share the amount around the same area, and try to have as much as possible to make it as a square shape, meaning a 90 degrees at each corner. Now at some part like these, you're not able to have that kind of situations because you are having a 3 neighbors, so one angle will be around 120 degrees. So you cannot really get like 100% 90 degrees for each quad, but want to make as much as possible to be able to go closer to a quad, square shape. And to do that, I'm going to do another feedback loop, but in this time more of a based on the idea of a physical particle simulations. Okay, control each point at the simultaneously, each in terms of the positions. Okay, so this is step 4, subdivide. All right, we're almost there. And I know that we are doing a lot of coding here. Yeah. And this too. Okay, now after doing all these, I might also want to get the naked edge points, which this one doesn't really have, so I think I can just leave it for now. And the first thing I would like to get is the normal direction of each primitive, which I'm going to use it in order to use the algorithm that I showed previously in the sketch. So normal, create the normal direction for a primitive, should look like these. This will be the axis, a rotational axis to rotate each of the point 90 degrees. Okay, and then let's go to create an attribute to each point. I'm gonna say attribute create. I'm just gonna create an empty attribute to each of the point as a vector, name as a direction, and this direction is going to be used to define which direction should the point move. Okay, starting with 0 now. All right, now I can try to do the steps. So you can use either a feedback loop like a solver or a for each loop. If you just want to get the instant result, then I prefer you using a for each loop. If you want to get the animation to show the smoothing happening simultaneously at each frame, then I would suggest using a solver. Either way, the things you're going to do is pretty much the same. So for now, I'm going to use the feedback loop, and later on I'm going to show how you can transfer that into solver. So this is the for each number. Going to again change this to a feedback loop by changing this feedback each iterations, fetch feedback. All right, now let's so there are two types of forces that I would like to implement to smoothen out the shape. One is this force to make the quad 90 degrees at the edge as much as possible by getting the average value, average point positions by rotating each of the point 90 degrees, the multiplication of 90 degrees, and use the average. The other way is to use the area, and based on the area value, move the edge point outward or inward so that all the faces share the same area. Okay, now let's do one by one. The first thing I would like to do is to apply this one first. To make the quad shape square as much as possible. Right? So let's do this. To do that, I am going to access to each of the primitive simultaneously, so I'm going to use the primitive wrangle. Okay, then let's name this relax. All right, so let's start writing code. And this is going to be the last code that I'm going to write here, which is going to be a bit long, but not that hard than comparing with the things that I did previously. So don't worry. All right, so first thing I would like to do is for each primitive, I would like to get the point positions in an order, maybe in clockwise or counterclockwise, maybe clockwise. To do that, I'm going to get the vertices out of the primitive, vertices number out of the primitive. So use the prim vertices, which will give you a vertex number in a clockwise order, I think. I think it was a clockwise order. So at prim num. If you use the prim points functions instead, you do get the point numbers which belongs to this primitive, but it is not in the order of the primitive. It might be really randomish in terms of the order. Could be 0, 1, 2, 3, or 0, 1, 2, 3, and so on. So, but for now, I want to get disordered vertex numbers or point numbers. So I'm going to first get the vertex number, then convert the vertex number into a point. That's kind of a trick. So I'm going to look through all the points. Get the vertex number, then convert it into a point number using vertex point. Okay. So, and then get the point position. At PT. Now, like I said in the sketch, what I want to do is to let's create some exaggerated geometry like these. So for now, I'm looking at this primitive number. Okay, and I have just retrieved the point number 0, 1, 2, or vertex number 0, 1.3. Okay, and let's say I'm looking clockwise. Okay, now at each point, starting from 0, I would like to rotate this point positions based on the center point of this primitive. Could be could be somewhere around here. Let's say this is the center point. Okay, and using this center point, I want to rotate this point at the 0 90 degrees, the multiplication of 90 degrees until it loops. So in this case, 90 degrees, rotating somewhere around here. 90 degrees again, somewhere around here. 90 degrees again, somewhere around here. So in total, you have 4 points from 1 points. Okay. And what you want to do is to do the same thing for all the other points. For this point, rotate 90 degrees, rotate 90 degrees, rotate 90 degrees, rotate 90 degrees. And this one as well, rotate 90 degrees, rotate 90 degrees, degrees, degrees. And this one, rotate 90 degrees, rotate 90 degrees, and so on. So as a result, at each of the locations, you have like in total 4 points numbers, 4-point positions. And with those 4 points, you want to get the average point positions. Somewhere here, 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 somewhere around here. And that is the goal position for point 0 to go, point 1 to go, this point to go, and this point to go. And this directional value is going to be the force to move the point toward that goal. So that's what I would like to do here. Okay. Now, to do that, for each points, I'm going to create a average point position named as APOS by copying the current point positions and do the nesting loop, accessing to another vertex list. So pretty much do the same for loop right here, changing the iteration variable, let's say n. Now the thing is, I don't want to want to start from n, but I actually want to start the n from I plus 1. Okay, so if the I is equal to 2, then I want to start the n from 3, because I want to use this n as a multiplication number for the angle. Okay, so if I have to do like this, then I also have to increase the target value, or target conditions value, because so that the total number of the iterations will be equal to 4. And in any case, okay, so that's the second nesting loop. Now I am going to get the vertex number out of this second nested loop, VT, VTS, n. Then, and the n value could be more than the length of the VTS. So if it goes more than the length of the vertices, then I have to make it back to 0. So I'm going to calculate the remains using the modulus VTS, like these. Alright, now I can get the point number out of this vertex point 0 and vt. And then I can get the point position and pos point 0 p and pt. Right. Now's the time to create a angle value so that I can calculate the angles. Rotate the angle, rotate the points by 90 degrees, okay, for each point. So let's use the integer count. Let's create the integer count before get it into the loop, and use this count to define the angle for each points that I'm going to rotate. So float angle is equal to pi multiplied by 0.5, which is equivalent to 90 degrees, and then multiplied by count. The first value for the count is equal to 1, so this is going to be 90 degrees in the first iterations. Okay, meaning what I'm doing here is to rotating the neighboring point. For example, if I'm looking at this point right now, right here, then I am rotating this point right here. Okay, and if I do the rotations with the positive number, it rotates counterclockwise. So this point will be rotating 90 degrees to this direction and comes somewhere around here. Okay, so for the next point, for the next point, this one, I want to rotate 180 degrees so that it can come somewhere close to this point, the original point positions. And for this point at the top, you want to rotate 270 degrees counterclockwise so that it can also comes somewhere around this point. So at each iterations, you want to increase the angle by 90 degrees. So I'm going to update the count, iterate, increment the count by 1 at the end of the loop. Right? Now, okay, sorry, I forgot to switch back to the Houdini's display. So where was I? Okay, I think it was started from here. So first of all, I have created the average vector positions, copying the current point positions. Okay, and then I have created this count value starting from 1, and this will be used to increment the angle. Okay, and what I'm doing here, if I visually explain, so let's say I'm looking at this primitive right here. Okay, and let's say when the I is equal to 1, the point where I'm looking at is this point. Let's assume this is the point that I'm looking at. Okay, now after getting all those point positions, I'm creating this nesting loop starting from n equal I plus 1, meaning the next loop will start. I'm still looking at the vertices, the number of vertices, so looking at the 4 numbers, 4 points, this one. But what I'm doing here is starting the loop from I plus 1, which means if this is the I, then this is I plus 1, okay? And until it loops all through. So I plus 1, I plus 2, I plus 3, I plus 4. And in total, you have 4 number of iterations for this nesting loop. And the reason why I did like this is because in the first n equals to I plus 1, for this point, I want to move this point somewhere close to this one by rotating 90 degrees counterclockwise from here to here. So using the center point of this primitive as an axis, together with the normal direction, I'm going to rotate this point like this, and the point will come somewhere around here. Okay, and the angle written right here is the value that I'm using to rotate this first point. Okay, now that's when the n is equal to I plus 1. If the n is equal to I plus 2, which could be somewhere around here, then in this case you want to rotate the point 180 degrees using this point as an axis. So 180 degrees, so that the point will come to the close to the original point positions retrieved right here. To do that, you have to increment this angle. So what I'm doing here is to multiply 90 degrees value by an integer value count, which is going to be incremented by 1 at the end of this nesting loop. Starting with 1, so the first loop you get 90 degrees, and the second loop the count becomes 2, so this becomes 180 degrees, and the third loop will become 370 degrees, and so on. And last, you have 360 degrees to be rotated. Okay, so by doing it, at any of the nesting loop iterations, all the points will be rotated to somewhere close to this original point positions. And by adding those point positions to this average point positions and divide it by 4, you'll be able to get the average point positions for this point and all the other points by looping through all the points using this first loop. I hope it makes sense. Now, let's do this. Now that I have an angle, it's time to create the rotational matrix to rotate the point. So matrix mat is equal to ident rotate the mat with the angle, and the axis that I want to use is the at n, the normal direction of the primitive that I have created previously. Now, in order to rotate the point, which is, what is the point that I want to rotate? The point that I want to rotate here is this one, this positions right here. So let's do that. But before doing that, we want to place the center of this primitive to the 0, 0, 0 position so that it can rotate using this center point as a center axis. So to do that, we first need to access the center of this primitive, which is at P of the primitive wrangle. Okay, so I am going to, I guess this is the point that I would need to rotate. So n pos minus the center, which will bring the center of the center point of the primitive to the 0, 0, 0, along with all the edge points. Then do the rotation using the matrix, then add back the center like this. All right. Now, after rotated the positions, after rotated the point positions, I am going to add this to a average point positions. And like this. No, like this. Okay. Okay, should be okay. And actually, this is not a loop of 4, but actually this was a loop of 3, because I only need to rotate 3 points for each of the points. So if I'm looking at this point as original point, then the only point that I need to rotate is this one, and this one. I don't really need to rotate this point because it's at the same point positions. So if I make +1, then you are accessing to 4 points. But since I'm just using I, I'm just accessing to the first neighbor, second neighbor, and third neighbor, and that's it. All right. So, which is good. So I'm just rotating 90 degrees, 100 degrees, and 270 degrees. And after leaving this loop, you have added those rotated positions to this average positions that I've copied from the original point positions. Now to get all the average positions, you just now have to divide this by 4. And that's it. Okay, I'm assuming I am only I'm only accessing to the quad. Since I'm using the subdivided right here, I have made sure that all the primitive has 4 vertices, so I think this is okay. If you're not really sure, then you could also say length of the VTS, which is equivalent to 4, so which either way is fine, I think. Maybe it might not be a good idea to hard code for some case you want to implement later, right? Now, now that I have to get the average point position, which is going to be used as a target point position in order to change its value, change each of the point to make it square as possible. Okay, so to do that, to use this, I'm first going to create the directional value going into this direction from the current point positions. So directions is equal to a pass minus the current point positions. Okay. Right. Now I could also normalize this one and multiply it with a distance of a pass and positions, which is pretty much the same as all the subtractions. But the reason why I'm doing here is because I wanted to convert this distance as a power of 2 to make it more like a force. So if it's closer, if it's this determines that if the distance is really far, then you have more force. If the distance is small, then you have less force. Like a log-like scale, which is pretty similar to how you create a spring force for particle-based simulations. And finally, you want to multiply with some coefficient value to control how much you want to apply this force. Could be in between 0 to 1. Maybe 1 could be too much. Okay, and then direction. And then what else? Okay, so that's the direction that I've just created as a force. And then finally, I'm going to add this attribute, add this value as an attribute to each of the point to the direction attribute using add option. So I'm not directly going to update the point position at this point, because if I do that, then if I update one of the primitive, then since we're at the primitive wrangle, at the different primitive, it's trying to modify its point position as well, and that will like collide to each other. That will like have the confusions to each other, which makes the result a bit skewed. So first thing I would like to do is to add all those forces into one point and gather it as a added value. And then after adding all those value into a point as an attribute, then use that to move the point simultaneously using point wrangle. So let's look at the result. Okay, I'm getting the error. Why is that? Let's see. A36 undefined initialized variable direction 36. I think I do have this direction. Why am I getting error? Invalid source. Let's see. Syntax error, unexpected end of line 25. This one. What else? What else? Reference to undefined variable k. Okay, I didn't create this k as a parameter. Okay, so let's do that. Float k is equal to chf. K. Coefficient value. Kind of a strength of a force. Okay, just do the job. And if you look at the geometry spreadsheet for the point, you'll be able to see this direction, which is equal to 0, which is a bit weird. Shouldn't be 0. Should have some kind of value. So I think something is wrong. Let me check. So want to check if the average position has been defined. So set point attrib 0 a pos at pt a pos. Do I have this pt? Yeah. Let's check. So I do have this average point positions, and it's different from the current point position. So I should be able to get the direction, and I know why, because I have set the coefficient to 0. Right. If I set it to 1, then I should be having some values for the direction. Alright. So this directional value is going to be used as a force to move the point. Alright. Now I'm gonna delete this one. Now, before just actually using this, I'm going to test this out with simple situations. Just getting one of the primitive and try to do the step for this one just with this single primitive to see how it works. Okay, so I have just calculated the directional value for this single primitive. So each point has its own direction, like these. Now what I'm going to do next is to use the point wrangle to move the point toward this direction with this amount. So at p plus equal to v at direction, and that's it. And let's see what happens. So I think something has changed. Okay, am I seeing any changes? Okay, I think it is changing, but something is not really wrong. If I change this value, I think I should be able to see some changes here, but I don't really see it. Okay, let's see why it's that. That is because I have to uh, because this one already creates the direction, so I'm going to ignore this one for now. And let's see. So I have created the direction, and by changing, I think I'm not sure if it's changing that much. Now to check this a little bit more, I am going to make the power to 1 so that you have more exaggerated result. So you can see that by changing the coefficient value, it's going from the skewed geometry to more like a square geometry, and becomes really square at the end. So I guess by looking at this, you might ask, why not then use power of 1, or just use this subtraction as it is. But when it connects with other primitives, then the power of 1 might be too strong at some cases, which might collapse, destroy some geometry shapes. So to make it safe, to make it like a spring force, further you get the stronger. If it's close enough, then you get smaller value. Might be a good idea to make it 2. But if it's just a single, then you don't really need to consider about those, because it's not connected to anything. But and the result, I want to create something like these, the squared mesh. Okay, so it's working. I'm just gonna bring this point wrangle to here so that I can move the direction. I'm gonna remove this one. And move points. All right. And I'm seeing some caches. Okay, let me reopen this. All right. Now, since this is a feedback loop, it's going to use the re-updated value for each loop. So let's see what happens. Slowly increasing the value. You can see that each of the face trying to become square as much as possible, but at the same time it's going to change the overall shape as well. That's not really what we want. So although each of the squares is trying to become square as much square as possible, that's good, but we don't really want to change the whole shape reference. So to keep the whole geometry profile, I'm going to project the point as soon as changing the point positions a little bit using this move points. So just gonna use this ray node for probably this original mesh, or to this subdivide mesh. Maybe to the original mesh is fine. So I'm going to create a null node named as orig, and then go back downward, accessing to the original mesh by using a object merge. Let's call it this orig, and accessing to the original geometry. Then project this point to this primitive so that it doesn't go off the profile with the minimum distance option. Now if I increase the iterations, it starts to collapse. The reason is because as I said, the speed was too fast, making the coefficient value equal to 1 in this case. So let's try to make this smaller, like 0.1. And now the movement becomes slower, which tries to create a bit more smoother result, or a better result, like 0.05, much better. But it's going to make the calculation slower, so you have to have more iterations to have a better result, like 100 and so on. Now this itself will create a square-like mesh for each quad, which is fine, but there's another problem here because those you can see that some of the squares have a smaller area, some of the squares has much bigger area, and also have some kind of a problem with these situations. Okay, which is not really ideal. Sometimes the mesh becomes too small and so on. That is because I'm missing one another constraints to keep the area as same as possible, as much same as possible, to make it pretty, to make it closer to the average area of all the faces. Okay, so that's the additional force that I would like to implement next. All right, so going back to the 0 iterations, going to add a additional force inside this relax. To do that, I do need to calculate the area beforehand for each faces and also calculate the average throughout the face. So measure node and calculate the area for a primitive, which will give you these area attribute from 0.02 to 0.001, right? Now, from this, I'm going to get the average by using the attribute promote for the area, for the primitive, convert it, promote it into a detail, get the average, don't delete the original, and name the average area as Ave area. Okay, so the average area is currently 0.01. So if the current primitive area is smaller than this, then I want to expand the face. If it's larger than this average area, then I want to shrink the primitive. And that's what I want to do in order to keep the area size as much the same as possible for each faces. Okay, and we're gonna do this inside this relax. It's not that hard to do for these one and compare with the first force. Okay, so let's go inside, and I'm going to rename this coefficient K, which is for the spring, which is for the to make the square. So I'm gonna name this K1 or K square. Okay, and I'm gonna add another parameter called K area from 0 to 1. Name this little case. Right. So K square is equal to K square float K area is equal to CHF K area. Okay, now I have to rename this K to K square. Okay, what do we have here? Initialized variable. Is it? I think it's been initialized. I don't know why. Okay, now also, let's also retrieve the average area as well. So float average area is equal to detail 0 average area. All right. Okay, so now that I have the average area, I could also calculate the differences between the current area and the average area. So difference area is equal to a current area subtracted by this average area. And if it's this positive, then you want to shrink because the current primitive area is too big compared to the average. If it's negative, then it's too small, we want to expand it. All right, so having those values going down and calculate another directional value. Okay, so let's call the first one to direction 1 and the second one as direction 2. And the direction 2 will be based on the area. And to do it, I'm just going to first of all get the directional value going from the center to to the current point position to the center. So center of the primitive can be retrieved by add p, and by subtracting by positions you get the direction value going from the position to the center. Now if I multiply with the difference area, and you will be able to get if it's positive, then that means you want to shrink, so that's the right direction. If it's negative, it's going outward, so that's the right direction. And then you want to, since this is the area, the units of the area is the length multiplied the length, okay? So you could, if you want to make the fast process, then you could get the square root, but like I said, it's a good idea to use the power of 2, the square of the value, the directional value, to make it as a force. So keep it as it is, it's fine, because this is already a power of 2 of the length. Okay, but addition to that, I'm going to multiply by 0.5 to make it a bit smaller, and multiply by k half area. This 0.5 is not really necessary, just based on the balance that I'm looking into the direction 1 and direction 2. Okay, now I have 2 directions. I can add those together. Direction is equal to direction 1 and direction 2. Finally, add it to the point. And let's see what happens with these. So I have to update this k square and k area. Let's update to this 0.2 and 0.2. See what happens by increasing the iterations. Okay, I still see some unwanted result. It's not that clean, is it? I think I'm missing something here. Let me see. I might need to do other step. Let's see. Let's see what I need to do. Okay. So I'm checking out what I have written. Okay. One of the reasons why I'm having this kind of a jaggy result is because I'm not resetting the direction value to 0 after I have calculated all these. Because I'm using the add option to increment directional value at each frame, it's keeping the last updated direction. So that's a bit of a problem. So I'm going to create an additional point wrangle to reset the directional value. Reset v at direction is equal to set 0, 0, 0. Now this should do the job. Okay, now it's more cleaner. Now let's try to increase the iterations, and you can see that it's become cleaner and cleaner by increasing the number of iterations. So previously, when it was 0, it looks like these, squarish, pointy. Now if I change this to something like 500, it becomes more smoother, much nicer iterations. I do see some kind of a problem here, flipping plane. Maybe I can reduce that by making the relax, the K to 0.1 and K area to 0.1 as well, to make the movement a bit smaller. Not so much. Maybe the original remesh parameter might help in this case, meaning changing this value a little bit by 0.6. Yeah, better. Yeah, looks nice. So this is kind of a final result that I was looking for, creating this clean, not that clean, but a desirable quad remeshed result. We're using these kind of algorithmic process. Okay, so this is the step. What was the step number? Step 5, was it? Okay, so step 5. Step 5, smooth. All right. So let me also try this out by increasing the resolutions of this remesh, like target size to 0.15. See what it does. Does need a little bit of calculation time, and it still creates the quad remesh like these, quad surface like these. Now, if you ever have used a plugin like Exoside Quadremesh like plugins, those plugins will create much cleaner faces, so compared to this result. So as I said in the previous initially, if you just need a result, just use those plugins. If you're really curious about the process, then this could be a starting point, I think. Yeah. Let's get this back to a 0.25 or 0.26. Okay. Now, going to do several more options to make it a bit more flexible. First thing I would like to try out is to change this to a solver so that I can create an animation for this smoothing step right here that I have, which is not that necessary, but just for fun. Right, so let's do this. I'm going to create this, and since I'm just going to use the same like network right here, it's pretty easy. What I'm gonna do is just copy and paste some of the stuff, and that's pretty much it. Solver, create a solver. And this is the original mesh that I want to smoothen out. Now, I'm also going to connect the original geometry to the second input of this solver, like these. And I'm going to copy all these network inside a feedback loop and just go inside the solver. Paste it. Oops. Connect it like these. And from the second input, I am having this original geometry. So connect it right here. And that's pretty much it, I think. Do I'm referring to any other stuff? Nope, not really. Okay, so with these, if I play it, you can kind of see how it iterates, iteratively smoothen out using these functions. Maybe I can increase the substeps a little bit to make it go faster. Yeah, just like these. So all those two forces are working great, I think. If I try to make some of the forces to 0, like let's say make the area force to 0, let's see what happens. I'm still seeing a better good result, but as you can see, the face area, sometimes the face area is too small compared to the others, like these. So the second force might really necessary. If I try to set the square force to be 0, let's see what happens. Now all the face is trying to have the same area, but now it's totally skewed. You don't really see any clean faces anymore. It does have the same area, but it also has some lot of problems in terms of its shape. So that's not really good. So combining those two forces makes really sense, I think. Okay, just like this. Not that good result right here. But overall looks okay. Right. Now I want to try out with all the other geometry other than this one, especially with the geometry which has the naked edge or the unshared edge, and see if it still works. So the easiest one I could think of is to create like a grid. So switch between the pig head and the grid. And then I'm going to use this for each loop to test out. Okay, now I'm seeing some caches here. Okay, now let's switch to the grid. Okay, the grid might be too big. So make this grid a smaller, let's say 2 by 2, 2 by 2. Okay, now I see that seems to have some problem here. It's not really dissolving any edges using this first loop. The reason is because this grid is totally flat on XZ direction, it couldn't calculate any principal curvature direction, and that's the reason. And let's see where we were calculating the curvature right here. So if you look at the geometry spreadsheet for the point, you get 0 or none. Okay, if it's all flat, you'll not be able to get any curvature value. So that's a bit of a problem. So we might need to create the condition when the length of the curvature is equal to 0 or none, then we're going to replace that curvature with other value. Could be random, could be the direction value of this edges, so on. Now I'm going to get let's say if the point of this geometry has curvature of 0 or none, then get one of the neighbor point and use that connected direction as the curvature, the virtual curvature. So that's what I would like to do here first. I'm going to create another point wrangle right here. Now if the length of the curvature is pretty small, close to 0, or if it's none, using is none function, you can check if it's none or not. Then that's when you want to add a additional some random curvatures. So what I'm gonna do is to get the first neighbor point using the neighbor function for ptnum, then get the point position at that neighbor point, and then get the direction going from this point to the neighbor point positions. Let's also normalize this and use this as a kind of pseudo curvature. It's not really a curvature value, but since I do need to dissolve the edges, I do need to have some kind of directional value. So let's assume that this is a kind of a fake curvature, and update the curvature with this direction. Okay, now let's check, and now I think I do have some curvature, and let's look at the dissolve result, and now I see that the edge has been dissolved. Maybe this is not really creating a clean just I'm gonna say, yeah, better. So this is the result of the dissolving, and this is the result of some fixes for triangles, and this is the result of the subdivisions, much better than the previous one. Then going back to this one, you can now see its result. Let's iterate 1,000 times. Okay, now other problem I see is that the edge has been moved as well. Edge of this geometry has been moved. Even though I have this ray node, it doesn't really fix the unshared edge positions. Okay, which might be okay at some situations, but if you want to keep the edge position as the fit to the original unshared edge, then you might need to do additional steps to do that. So let's think how we could do that. Okay, so to do that, first thing first, we need to retrieve the unshared edge from this original geometry. So let's try to get the outline by using the divide node to first of all dissolve all the unshared edges, or I mean the shared edges. Then use something like primitive node to get the outline, like these. Right, so this is going to be the geometry that you want to use to bring those edge points to here. Okay, so probably using another ray node only for those outer points might just do the job. Okay, so to do that, you do need to get the group informations, or you do need to get the point information, which points belongs to the unshared edge. So you can get that by going back to somewhere around here, and creating some group node for the point. Let's name this naked and disable the base group, and instead I'm going to enable this include by edge and check unshared edge. As a result, you'll be able to create a group for all the points which is at the unshared edge, at the naked edge. Okay. Now going back and create another ray node. Anywhere is fine, I think, but maybe I'll just do it the last. And for this one, I'm going to move this point, then set this to minimum distance again. And the point which I want to ray project is naked. And this is the collision geometry. Conveying just a second. Then connect it right here. And as a result, you'll be able to get this edge being connected to the unshared edge. And another problem, one last problem I have is the corner point. I do want to keep these corner at the pinpoint right here. I don't really like these, like and this point being off a little bit from the corner. So let's also fix that. To do that, I am going to create a point wrangle, maybe after a reset, and name this pin corner. Okay. Now what I'm going to do is to check the current point positions coming from here, and also define which point is at the corner by having two references, one from this corner edge and one from the original mesh coming before doing any smoothing. So this one. So I'm going to compare with this one and this one and check if these current point positions are sharing one of the point on these edge right here. Now to do this, I might want to like dissolve all those points in between, which shares a straight line right here. So I think I don't really want to have those points in between when it's straight. So I want to remove that. But I think someone told me in some other streaming there's a fast way to do this using some node, but I forgot what that is. Polypath, if anybody knows that, let me know. But since I cannot remember what that was, I'm just going to do a wrangle way. Okay, to do it, I'm going to use the point wrangle. Dissolve point straight. So to do that, just get the neighbor points from each point and then see if the dot product between those two direction going from point to the all those two neighbors is equal to 1 or 0, or equal to 1 or other value. Okay, so int neighbor num, and I'm assuming that there's only 2 neighbor points at each point. Point neighbors. Point okay, just neighbors. Forgot. Okay, assume there's only 2 points, so vector position n pos 1 is equal to 0.0 p nays 0 vector n pos 2 0.0 nays second point. Then get the direction and pos 1 minus the current point positions, and vector direction 2 is current point position minus n pos 2. Okay, oops. And then also normalize this because I want to calculate the dot product. Normalize this. Then if the dot product of this direction is close to 1, then that means it's straight. So that's the point that I want to remove. So if it's close enough to 1, meaning I could say more than 0.99, then remove that point. Okay, I think I did something wrong. So did it really moved? Nope. Didn't really removed. Okay, let's see what was wrong. So vector neighbor. Why am I using primnum? It has to be ptnum. Okay, now the straight the points at the straight line has been gone, or you only have received a point on the corner. Okay, disconnect this, and I'm going to connect this one to the second input of this pin corner, and I also connect the original geometry, which is this one, to a third input of this pin corner right here. Okay, almost there. Now I'm going to retrieve the positions from the third input. So let's say n pos is equal to a point, and the point number doesn't really change from the first input and the third input. So what I can say is 2p and ptnum. Okay, now I have just received the point positions from this geometry. Okay, and what I've looked like to check is checking each point at this geometry and get the closest distance between this naked edge, especially with these points corner. And if the distance is close to 0, then that's the point you want to fix. That's the point you don't really want to move. So going back, and to get that information, you can use the new point function, new point for the second input with the n pos, and get the near positions at npt, and calculate the distance between the n pos and the near pos. And if the distance is small enough, like close to 0, then that's the point you want to fix. So I'm going to fix the point position to the original n pos positions. And as a result, okay, it's not really changing. Let's see why. I'm not sure if this is working. What if I don't have these conditions? Wait a minute. I might need to do this after every ray node has been done. So I think I'm gonna connect it like here, connect it like this, connect it like these. Okay, although it's not really changing its positions. Okay, now it does. Now seems like the distance, it's not really, maybe 0.01 was too small, I'm not sure. What if I make it 0.01? Nope. Okay, so I guess something must be wrong here. This one. It has to be 1. Okay, now it's gone. Okay, now I think it's fine. By increasing the iteration, it doesn't really change its corner positions or the side positions. I think starting from 0. Starting from 0. Slowly increase. Doesn't really change the side or corner. You can just increase as much as possible. Alright. Looks nice. Okay, so let's try to bring this, what I have implemented, to the solver as well. Just gonna delete all those stuff inside the solver and recopy everything, because that's easier. So this one so this is the first input, this is the second input, third input I mean, and this one comes actually I don't really need to input here because I can get it from the first input. So I guess that's the old informations. Now I'm gonna copy all these, copy it, go inside the solver, paste it, connect it. Now the original square comes to the first ray, right? For the second ray, I'm going to connect this. And for the spin corner, so for the second input, I'm going to connect this unshared edge right here. And for the third input, I'm going to connect this original geometry like this. And now you'll be able to have the same result as the feedback loop. And let's see. Okay, so if I play it, you can see smoothing out based on the time. At some point, it just stops. Like this. Pretty satisfying, I think. Yeah, if you want to make these faster, you can always increase the coefficient value for the relax, like these 0.2, 0.2. If I make it 0.5 and 0.5, should be fine for the grid because it's a simple shape. Yeah, going faster. All right. So originally, the geometry looks like this. Then make it based on the remesh node right here. I have converted into a quad mesh like these. And this is the final result that I wanted to show. Right. And by doing this way, I think this can be worked for any kind of geometry. Let me check that. I'm going to bring another test geometry, which I didn't really use yet. Maybe like a squab. Let's see what happens. Let me make this squab size a little bit smaller, like 0.8. Okay, and switch this right here. And if I play it, it's okay. Well, maybe I can increase the size a little bit. I think I do need a little bit more number of quads. A bit more. Remesh to 0.15. Okay, then if I play it, create this kind of a quadrilateral mesh from any input geometry, considering the principal curvature and all the other tricks that I'd shown. Okay, so that is pretty much. This is to show some first step process to deal with a quadrilateral remesh, which is not really a perfect solutions at all, but as a geometrical process interest, maybe this is interesting enough to dig in. Maybe you could start developing your own custom algorithm based on this one, or maybe further from this one. And there are a bunch of papers writing about this quad remesh in different method, more sophisticated method. So probably looking at those is more helpful for you if you want to have more sophisticated result. But this could be a starting. This step could be a starting point to understand why you really need principal curvature for, and so on. What you mean by split and collapse and so on. You do need to do similar like steps to do the remesh thing, and maybe different algorithm in other papers. Okay, so that's pretty much it. Thank you for watching. It's been like, wow, this was really long. This was like spent like 4 hours, and yeah, I hope you find it interested. Not sure if it's not really like a cool motion graphics or anything. It's just some geometrical analytical stuff. So some people might find it really boring, but I find it myself. It's pretty interesting to do, so I wanted to share it. Okay, so this is it for this weekly tutorial, and I would like to do other stuff next week with different topic. If you're interested, please join. And if you like the video, I would love to have your likes and subscriptions if it's possible. And I'm also doing a Patreon myself, so if you are interested in supporting me, I'm always appreciated. You can go from the video description page of this video for the link. And I am also going to upload the file that I've just created in the sessions, so that anyone can see, download it, and use it for your own purposes, or in study purposes probably. And so yeah, after I have finished this live stream, I'm going to upload the files, and you can access to this file from the same video description page of this YouTube video. And I'm also going to keep this video as an archive so that everyone can watch it later. Okay. So I have a question saying, what if the mesh is not regular in size after triangulation? Yeah, that could happen, especially if you use like adaptive remeshing. which it still tries to keep the square faces at the same as much as possible, but sometimes those forces are not enough to make all four faces at the same size. So as a result, you'll be able to have a kind of a gradient square size based on this initial triangular mesh. So I'm going to show you how it looks like. So instead of using some normal remesh, I'm going to try to do the adaptive remesh instead, which will create this kind of a irregular triangle face sizes. Now this is currently too much in terms of the numbers, so I'm going to reduce it. Okay, this doesn't really reduce the number, does it? Gradation, well, maybe I can do it like this. Okay, so now I can see that I see a lot of triangles at these small areas, and I have a big triangles on those areas. Now let's try with these, see what happens. Connect it right here, and let's go with the solver. Now it's taking a little bit of time to initially calculate its dissolving area and subdivisions. Now most of the time the dissolving part takes a little bit of time as initial setup, initial step. Let's wait a little bit. Okay, now this is the result. And if I play with the smoothness, you can see that you still see some gradient size differences right here, which comes from the adaptive mesh. It still tries to keep the area size the same by using the force that I have implemented, but there are some limit to that. So create this kind of a gradient square mesh, if that makes sense. Which could be visually useful for some cases. I'm not sure in what cases, but I do see a lot of hard stuff going here. Maybe the steps is too fast in this case. If you're having a lot of like collisions like these, you might want to reduce the speed a bit slower for the K, especially for those small parts. Right. I hope it makes sense. Alright. Now, if you have any more questions, I'm happy to answer it. If not, I would like to end the session right here. Okay, I'm gonna make this back to a original mesh. Make this back to big head. Let me try with this adaptive big head. This may create a bit more cleaner result. Play. Yeah, I see some problem here. Maybe I might. One of one of the other reason I could think of why this kind of things happens in the small areas is because I'm using the average area to define the how fast it should go to the specific direction. So if you are using adaptive, you might want to make the speed as small as possible, and also maybe you can increase the power of the forces. So if it's smaller, then make it much slower, like this part. Make it like 4. Yeah, it still creates a bit jaggy edges. Maybe you might need to reconsider the force for the area in this kind of situations. Oh, maybe power of 1 makes it better somehow. Wait a minute. The one that I did is for the square. This is not the one that I wanted to change, but actually you can create the power of 2 for this area. This is what I wanted to change. Okay, yeah, I think it's getting a better result. Yeah. So, I hope it answers your questions. It looks okay. Yeah, clean. But I am going to keep this one for now. Alright. So I guess there is no question, so I would like to end the tutorial live for this week here. Thank you for watching and all the comments. I really appreciate it. And hopefully I'll be able to see you all next week as well. I'm gonna try to come up with the other topic that I found interested. Or if you have any topic you want me to cover, please add some comments to the video, then I would consider try to do that as well. Or you could also ask me at the Patreon as well. Okay, that's pretty much it. Okay, so thank you and good night. This is around 2 a.m. in Japan time. It's time to go to sleep. Okay, I'm gonna upload the file before I go to sleep, so hopefully you'll be able to get downloaded in a few hours. Alright. Good night. And see y'all.